I was like, seriously.
Okay. Okay. Are you ready for a quiz?
Tomorrow, today?
Oh, today? Only time. Before the related traits and the approximation.
Before approximation.
Yeah. Before the
From?
only chapter 3, but before the related traits and linear approximation.
Linear what?
Chapter 3.
Chapter. Yeah, basically everything before relative rates.
Yes. Before related traits.
So it includes differentiation and infinite fragmentation. Alright.
Okay. So I think this is on Saturday class, right? So we have the first derivative test, and the conclusion are we're going to have an increasing function when the first derivative is positive, and we are going to have a decreasing function when we have the first derivative negative or less than 0. Okay? And when it's equal 0, we know that this will be horizontal slope, right? Okay, now we go to the next one, and I would like to start with this. Okay. So yeah, this is summary from the previous one. Okay, just to make it more clear and I think good in arrangement. So yeah, this is the conclusion. Okay, the conclusion. So you have a local max when the f prime change from positive to negative, from negative to positive. Basically, how you draw the graph, right? So this might happen like this. So for example, here's positive and a negative and a negative, positive. You will see that it has maximum, minimum, right? And here we have an increasing function, and then it's say 0, and then it's positive. It means it doesn't have any maximum or minimum. Or it goes by negative and then 0 and then negative. It also doesn't have any maximum or minimum. Okay, I think this should be okay, right? Okay, now the next part is the second derivative. So before we go through what is the second derivative test, imagine these two curves, right? So consider the curve on the left and the curve on the right. If we think through the slope, both are positive, right? Positive. And we could see that if we maybe take some points, maybe let's try from the left one here. We take some point here, become like that, and then that one, right? Okay. Imagine that from nearly 0, it starts slowly getting up, right? Getting steeper, steeper, and steeper. Okay. So you can imagine that from 0, we add some value, we add some value, some value. Okay. But here, on the right side, if we add the tangent for some points, let's say from here, you will see that we start at a steep one, right? And then it's becoming lower, but it's not negative, it's lower, and then maybe nearby the point B is nearly horizontal or nearly 0. Which means as a value, it's getting decreased, right? So we could see that we have some differences between the left curve and the right curve. Okay? The best way to take these differences are the left one, all the tangent, the red one, is always below the curve, right? imagine this is the blue one, and this red curve is always below. Let me write clearly. This is getting here. This should be here. Okay. Should be here. Okay. And if you compare with the right one, this red color, the tangent, is always on the top. This we call concave upwards. The right one we call concave downwards. Okay. Or my suggestion to differentiate these two curves, you can imagine with a C. This is going up, going down. Okay. Going up, or you can add some arrow. You can add some arrow that this is going up like that. And this is going down like that. So whenever you see any curve and you see that you could somehow make like maybe nearly equal to C, then oh, this will be upwards and the other one will be downwards. Okay. Okay, basically that's the definition here. Blah blah blah. If the graph f lies above all tangent, blah blah blah, it's concave upward. But I think too many words, not necessary to memorize. Okay, I think you could just your see it upwards, downward. Okay, easier. But the basis definition is the base is on the tangent. You compare the curve with the slope. If the slope below, then concave upward. If the slope is on the top, it will be downward. Or you could stick with your C. Okay. Now based on that definition, then if we have this, just a random function, and we don't know what the function is, and we don't really want to know what it is, you can see from x equal a until x equal q, we're going to see several concavities. We say concavities. You'll see here is this. It means it's downward. Okay, we can say that this will be downwards. We can write concave downward. We'll write CD, and then from this point B to C, it's up, right? So it's upwards. Or if you would like to add an arrow and then change the direction, and then after that you can see that somehow at this point C, from up it's changing the direction, right? It's become like this. So from here, and then suddenly it changed. So it's going down, right? It's going down. And then we have some tip, some corner, but doesn't matter. We only see the concavity now. It's going up again, right? And then here, still going up, right? It's going up. So we're going up. So up. This is concave upwards, and then still from E to P, still upwards and then downwards. So upwards and downwards. Okay, now how to test this is actually based on the second derivative. Whenever your second derivative positive, we are going to have concave upward. Okay? Whenever the second derivative is negative, we are going to have downward. Okay? So upward is for positive, downward is for negative. The second derivative. Okay, second derivative. So what does that mean and how it relates to our first derivative? So if we remember that, for example, this point B and point C, okay? If we just take the slope, okay, take the slope, and then after here, let's say this is 0, okay, and then it's going negative, 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 but then somehow it's adding some value that change in value. We call that an inflection point. Okay, so we call this point B here, it's inflection point. Basically, an inflection point is where the concavity changes, okay? Either from downward to upwards or from upwards to downwards. So this point C also another inflection point. Okay, so this is another inflection point. Somehow, inflection point can be assumed, but it's not necessarily true, that the second derivative, it might be equal to 0 in inflection point, but it's not always true. Okay? Let me write. We can assume at first, we can assume that this might be an inflection point. Or if it doesn't exist, like this one, it doesn't exist, right? As a slope, it doesn't exist. But perhaps we could also say that it can be an inflection point. Or f double prime doesn't exist. These two possibilities, again, it might be an inflection point. So whenever we change the concavity, then that point is, we call it inflection, the point of inflection. Here, you can see the definition here. A point P on a curve is called inflection point, blah, 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 if the function continues. And the curve change. And then, from this second derivative test, we could draw another conclusion. Remember that in first derivative, when you have first derivative, right, you can have like positive and then 0 and then negative. We say it's maximum, right? And when we have negative, 0 and then positive, we say it's a minimum, right? Now, how about if we know the the first derivative, and we also know the second derivative? We can also relate those connections with this. So whenever we say that we get the critical number or critical point, the f prime c equals 0, that c is the critical number or critical point, and then the second derivative, it's positive. If the second derivative is positive, f has local minimum. If the second derivative is negative, the f has local maximum. This is also true. So you can have at least two possible ways to check the maximum and minimum. You can check the line number with the first derivative. You check plus, minus. Oh, you get plus and then minus. It means that you are going to have a maximum. Or you could go the minimum one. Or you could try the second derivative. Whenever you have the second derivative positive, it will be local minimum. Or if you have the negative one, it will be maximum. You could check. I think I didn't put any. Yeah, I forgot to put the picture. So let me just draw. That's simply by this function we could see why this is always true. Okay. So let's say we have that. Okay. And then we have here. Okay, let's say this is our C. Okay, this is C. So we say that here is when our slope is 0, okay? Or the first derivative is 0. So let's say we have our f, okay? And this is point P. This is concave what? Upwards, right? Concave upwards is when second derivative is positive or negative? Positive, okay? Second derivative is positive, f has local minimum. Local minimum, right? The same way when we have the maximum one, it's downward, which means it's negative, right? The second derivative is negative. Okay? So let me write here. This is concave upward, which means the second derivative is positive. And the same way with the concave downward. And this is for concave upward. So you have a function, you know the first derivative, you know the second derivative, you can directly, immediately determine the maximum or minimum value. Okay. Any question first? Any question first? So remember, our goal in this chapter is basically we have a function and we need to draw the function based on calculus. Based on calculus. So how to know what is the unique property of the function? For example, the property will be, is the function decreasing, increasing, or how is the concavity? And somehow if we know at least if we know the first derivative, we know the slope. If we know the second derivative, we know the concavity, how the curve will change the concavity.
Can we go back to the first derivative test? I have not taken it before.
Oh, okay. This one, right?
Yeah, that one.
Okay. Okay. Now, let's go for some examples so that you can have more visuals on how to know the first and second derivative test applications. Okay, let me put. So let's say we have this. So we start from something simple. The goal is perhaps let's sketch the curve. So first we need to discuss on concavities, inflection point, and then local max or min. So how to sketch the curve is basically we are going to start from here. Actually, we need to start from another section, but let's say if we are going to discuss this first. Okay. So we have the function that we can derive easily, right? So let's say we are going to derive until the second derivative. Okay. So let's derive for the first derivative. This will be 4x cubed, right? And then negative 12x squared, I think. And then the second derivative is 12x squared, and this will be negative 24x. So first we could find from the first one, we could find the critical numbers, right? So we set up the first derivative equal to 0. Okay. So basically we are going to have this equal to 0, and then we could take that, right? or maybe this is 4. Okay. Maybe answer first. Okay, so from this we get that x equals 0, x equals 3. This is the critical numbers. So perhaps if you want, we could draw the line number and find out what it is. Or if you want to try the second derivative directly, also okay. But I would like just to draw how to show you how to find or to prove the first derivative test. Okay. So first take the line number and then just put the point. Put the point 0 and 3, and then try the intervals. So try the intervals. You can try, let's say -1. -1, this will be negative. This will be positive. Positive, negative is negative, right? And then try x equal 1. So x equal 1 is, this will be negative. And then positive. So it will be another negative. So it's still decreasing, right? Still decreasing. And then try above 3 is 4. So let's try 4. 4 is, this is positive. This will be positive. So positive, positive is positive. So we don't care much on what exactly the multiplication is. We only care about the signs. Okay, we only care about the signs. So we know that it will be decrease. So decrease, decrease, or maybe just that, and then increase. Okay, but we are not sure yet what kind of graph. Okay? We need to check with the second derivative, which we are going to get, or expect. Our expectation for the second derivative we are going to get, is it going to be like this, concave upwards or downwards, okay? And which part of the interval. Okay. Okay. So we take the second derivative, and then we can take the second derivative and then take it, equaling it to 0, because it perhaps that will be our inflection point. Perhaps it might be our inflection point, and then we could try the x equals 0 and x equals 3. So we could try, for example, if you want to check the maximum minimum through the second derivative, we could check f0, and then this will be 0. Maybe let me write this first. Okay, let me write this first. Later I will take that. And then we check 3 to our equations. Maybe calculate a little bit. So 9 is 108. 3 is 72. So it should be 36. So this will be positive. So second derivative is positive. It means it's concave upwards at this point. Okay. So okay, no information about the 0. Okay, so it will be concave upwards means it's minimum, right? So local minimum, and it appears similar to what we have here. Okay? So this is, you can go here or doing the line number. So after you get the critical numbers, what you can do is you can check the critical numbers, put into the second derivative test. If this equals 0, we don't have any conclusion yet. Okay? But if this is positive, we know that it will be concave upwards, right? So I think let me draw here. Let me draw conclusion here that this is going to be like that, right? It is concave upwards. So we know that this point here is local minimum. Okay. Or we can draw a line number and then test the interval and then. For me personally, I'm usually using the line number because I can get the feeling of what kind of curve, since I can imagine this is as the x, and I can imagine at what point there will be something, maybe some change in the graph. Or you could still going through this one. It's still the same result. Okay, the same result. Okay. So this for the left one here, no information yet. Okay, now let's copy the second derivative and we check the concavity. We check whether we have an inflection point or not. So let me write here. So to check whether it has concavity or not, we can imagine that this is going to be equal to 0. Okay. Suppose that we are going to see some inflection point, and then we solve this equations. Okay, and then we get that we have another numbers 0 and 2. And then we can check the 0 and 2 with another line numbers. So remember, the first line numbers, this is for the first derivative. The second one here is the second derivative. And the way we are doing it is the same. So we check the intervals and then check the second derivative. Okay. So check the interval. Let's say start from -1. Okay, I think the easy one here. -1 to here. It's negative, so positive. Okay. So positive here, right? And then 1. 1 is negative. Right, 1 minus is negative, and then 1 positive, negative, right? So negative, and then check 3. 3 will be positive, right? So we are pretty sure that it was going to be positive, negative, positive, which means this is upwards, downwards, upwards. So every point here, so 0 and 2, it will be our inflection point. Okay. So we say that this will be CU, CD, CU, or like that. And then we say that the inflection point, let me write here, inflection point is x equals 0 and x equals 2. Oh, I forgot to write the local minimum. Check the value on the original equation. Check x equals 3 on the function. The function is x with power 4, right? So check the local mean when we put into this. Okay. And then what is left? 27. This is 81. 27, 4 is 108. So 108 27, right? 108, right? It's 27, right? Is negative 27. So we know how to put our points. Okay? So this much. Okay? I think if you draw like in the exam, you don't need to precisely like unit per unit. Like you get 50, you were drawing like really huge. Just mention the numbers, okay, the numbers, and then the proportions. Not necessary to be exact proportions. As long roughly you draw correctly, I still give you points. Okay? I still give you like it's correct. Okay? So like for example, let me just draw what we have here. So we have I think since we have negative 27, maybe let me draw that. Okay, this is 0, and then we have 1, 2, 3. Okay. And then you can check several points. You can check also the F0, but I think F0 will be 0, right? So the point is always here, and then you can check F2. So 16 minus 32, it's minus 16, right? So it's already on the bottom part. So I think I will just imagine that 16 will be here and 27 will be here. So this will be 16. So see what I'm drawing here. It obviously is not proportional, but for the whole purpose to understand the curve, let me just write like that. Okay. It says that we have something concave upwards before 0, okay, and then it's supposed to be decreasing. So we are going to see, and it should be crossing the 0 because at the x equals 0 is 0, so we should be crossing this. So the only possible way is to draw something like that, okay, something like that, because after 0, it's supposed to be downwards. So we're going to do that, and going to be something there, right? And then it's going to be concave upwards. So let's draw that. So hopefully I can draw at least like that. Maybe not really good. Maybe it's okay. Maybe still not good. Okay, maybe that's better. And then drawing that, and at this x equal 2, remember we need to change from downwards to upwards. So we are going to get there. Okay, so this will be on the local minimum. Okay, and then going up. At this point here, you can confirm through the intercept, but I didn't mention about that. Later I will explain to you with, in more detail. This is just an introduction how to sketch a curve. So perhaps this is our curve, okay? So we have, this is concave upwards. So this is concave upwards, and then this is concave downwards. This is concave upwards. I think it should be should be here. But anyway, this should be, I think, 4, right? This should be x equal to 4. Negative 1, negative 2, negative 3. Negative 1, negative, negative, multiply with negative. Okay. Yes?
How do you know if it's a upwards or downwards?
Positive, negative, positive.
Also just plug in
Upwards?
the
Yes, plug into the secondary derivative. Yes. Testing the some interval.
So if you get positive, then it's
Upwards, yes. And this point, it doesn't necessarily to be the inflection point. If this is, for example, plus, plus, minus, so this will be not inflection point, but this is inflection point. Okay. You can test the interval. Okay. Okay, so far so good. So far so confusing.
I understand everything until the graphic. The graphic and then.
Yeah, the graphic I will tell you more about in detail because I skipped some process. We should have include how to involving the domains, the intercept, asymptote if it has an asymptote, and then we can start from first derivative and second derivative. So actually, you can start by taking the intercept first. What kind of x that should the graphic has? For example, it should be crossing 0, and this would be 4 because it's 2. Have I uploaded some questions on the previous semester? Not yet. Okay, maybe after your quiz, so you can concentrate on quiz. We can use two methods. We can use second derivative, or we can just take the line number, the same conclusion. Okay, any other questions? Okay, now yeah.
You said that the 0, like we're not sure what it means yet for like the second derivative method.
Yes.
Can you show us an example where it means something?
Yeah. I think if it is, for example, let's say if the 0, if it is going to be like that, it's upwards and then upwards, so it's positive, positive, and it's like a corner like this. It might happen. So we don't say this is inflection point. Okay, just that. Okay. So like the example here, like I show you, like we equate this to 0, but the point that we get, it doesn't really necessarily to be inflection point. We need to check. Okay? We need to check. When we find that it's changing the concavity, we say, oh, this is inflection point, this is inflection point. Okay? Right? And then what I say about the no information about this one, this is second derivative to check the local max or local min. If the local, if this is positive, it means like this, right? So this will be a local min. But if it's still 0, we don't have any conclusion if this is max or min. Or maybe it's not max or not min. Like our graph shows that it's true. This point is not maximum, not minimum. Right? Okay. Okay. All right. Any other questions? So besides the sketching the curve, another point that we are going to observe is how we can know from the graph, like the estimation of the first derivative or second derivative. Okay? So for example, okay, I prepare a picture and the questions here. Okay. Suppose that this is a curve, and it can be any. It can be function. It can be the first derivative. It can be second derivative. Depends on the question. Okay. So our goal is to find which one is the inflection point. Okay. So in each part, state the x coordinates of the inflection point. We need to state at x equal what number? Okay. Let's try number A. If the curve is f. So let me copy, make it 3. Okay, let me copy. Okay, so first, if this is f, which one is our inflection point? Remember, what is inflection point in curve? We just play out with our hand. So we see that this is concave downwards, upwards, downwards. And then we can see maybe some specific part on the point, and we can just make assumption to make it easy. Okay, so 2, 3, 4, 5, right? So let's say this is 1, 2, 3, right? So this is concave downwards. Let's say it's going to be this one. To make it easy, let's say at 3, okay? So at x equal 3 is inflection point, or maybe inflection point is when x equal 3, and then this is concave upwards. Maybe up until there, and then let's say 5. Okay, and then it's supposed to be 5. Okay, and we have here is and x equal 5. Okay, get it? Okay, right? For this one, okay. Just play with our hands. Now the next two questions is a little bit difficult if you cannot separate which one is a function and which one is the first derivative. Okay? So let's imagine if the f, this f here, we change to f prime. Okay? Which means that the same graph is the same graph, but we say that this will be our f prime. Now which one is our inflection point? Okay. Any other idea? See, you got good thing there. Okay. So what is inflection point? Okay, let's break for a while. Okay. Okay. We're back to the reality. Okay, back to the reality. You sleep. Okay, let's go back to our curve. Okay. So this is the first one. Okay, if the curve is f, and let's change to the f prime or the first derivative. Okay. So the inflection point is, it might be inflection point when you have your slope is 0. Right? In this case, the second derivative is 0. So if this is f prime, then the second derivative is the slope, right? The slope 0 is this, and this. Okay. So in this case, we can write inflection point is at x equal 2, x equal 4, and x equal 7. 6, sorry. Okay, this is f prime. Okay, let's change with another one. So this is going to be, let me write here that this is slope 0 here, slope 0 there, and there. So let's try another one. Okay. If the curve is f double prime, which means the curve is already in the second derivative. Which one is the inflection point? Which one is the inflection point? Yes. Okay, which one? Yeah. 6. Why? 5.
The inflection point is where like the curve changes from the upward to another downward one.
Yeah, correct. But this is not f. This is f double prime. How do we find it? 1 and good. It's 1 and 7. 4 not included. Do you know what? Okay. So remember, inflection point is. So remember, we have f. We say this is concave upwards, right? We have this. We say concave downwards, right? Inflection point is when we have changes from upwards to downwards or from downwards to upwards. So which one is positive? Is positive? Negative. Okay? So let me write here is the positive, this is negative. Okay? So at x equal 1, we see it's changing from negative to positive. Okay? So it's changing from concave downwards and then concave upwards. So we say that at x equal 1, f prime change from negative to positive. Okay? At 4, it's actually the slope 0, right? Or we say it's actually crossing the 0, but it doesn't change anything. It doesn't change it. Okay. So we skip 4. We see 7. 7 is changing from positive to negative. Okay. So right here, at x equal 7, f double prime changes from positive to negative. So perhaps if I give you another random function and we can imagine the function can be f, f prime, f double prime, and then if the question is asking the concavity or the inflection point, you need to be able to observe it. So basically, the first thing you need to remember is the first derivative will give you the slope and maximum minimum value. The second derivative will give you the concavity. Okay. Okay. Yes. Number 2, which one? Oh, this one? Oh, yeah. Maybe let me write. Let me give you some clue and some notes here that I didn't write. This is local max, right? And here is local mean, which means that local max These notes only apply to this question, okay? Because we imagine that this is f prime and this will be f double prime. You can imagine that this is actually the notes for if this is function, this is the first derivative. Or you could think this is the first derivative of the curve, okay, which is the f double prime. Do not mix up with the original default definition. Okay, I hope you understand my point. Okay? I hope you understand. Okay? Sometimes you see the notes here and you get mixed because you see, oh, this f double prime changed from negative to positive. No, it needed the first derivative of the curve. Okay? The first derivative of the curve. Okay. Okay, we can move forwards to the sketching curves.
Bisa Mak? Mau tanya tuh ada nang ulangan kuis ya? Ini kan dibaca ini.
Terserah bebas.
Ya kalau ini kan pasti ini. Terserah.
Bebas. Okay. I think we can go forwards. We go back to the sketching curve, but we are going to get into more details, okay? So this is my suggestion and guidelines. So every function, you need to consider domain, intercept for x or y. Is it symmetrical or not? Asymptotes, if there is any asymptotes or not. Interval of increase or decrease, and then local max, local mean, which means this is going to be the first derivative. Okay, this is going to be the first derivative. And then inflection point and concavity, this is going to be second derivative. And then finally we can sketch. Okay. So the most probable for a function to have all these terms is a rational function with some sort of restriction in domain, so that you can have some at least particular asymptote, and also for the domain itself. So you need to include whenever we have maybe some hole, okay, or maybe some discontinuity in the function. The whole or the complete answer is if we can write all of this clearly. It doesn't mean like your sketching need to be really good, but you can point out which one is the special point, which one is the unique property of the curve. Let's go for example. Okay. Or maybe let me write first. Symmetry means we can have even function or odd. Even is if we take the negative x inside the function, this will be the same. If we take the odd, this will be giving you negative. Asymptote, we have at least two general asymptotes. We call this is the vertical and horizontal. Okay, vertical asymptote, if we have some limit, I will write the infinity with terms positive, negative. Okay, so it can be works both ways. Okay, we say it's still the same. It is the vertical asymptote. Okay, the horizontal asymptote, if we have limit and we take x higher and higher, and if it is getting consistent at L, then it is our horizontal asymptote. And it works both ways, to positive infinity and negative infinity. Okay. For domain and intercepts, I think it should be clear, right? Or still confused on what is domain and intercept? Domain is, you can read your function notes. What is intercept? Yes. So intercept is, we need to find any points that when y is 0, we need to find x, and then when x 0, we need to find y. Or it means that the point where your curve will crossing, either for the x-axis or y-axis. That the intercepts. Okay, let's start directly with some examples. Okay, so we can know how to sketch the curve properly. Okay, so we have this curve y equal to x squared over x squared minus 1. We start by takes the function into domain. So let's write y. Let me write here. So the domain will be x squared minus 1 should be not equal to 0, right? Agree, right? So domain, let me write here, domain is or if we solve this, or, let me write or, the domain is, we can write interval. Maybe let me make it smaller. Or maybe let me write over. Okay. Either way, the same. Okay, you write x not equal plus minus 1, or you write the interval. Both are the same meaning. Okay. Okay, so that's domain. And then intercepts. I think for both x and y, they are going to be 0, right? So when x 0, then y 0. And I think 0, 0 will be the point that you are looking for. Okay. So x intercept and y intercept, both 0. Okay. And then check the symmetry. Sometimes symmetry is not really that important that you can skip, but we can check anyway. So we can check f negative x and from the formulations we get that this is going back to the original equations, which means that this is even function. You can relate even or odd with some function that easy to observe, like x squared or x cubed. I think that's the very simple function that we can think. The x squared is having the same left and right, symmetrical, right? For the x cubed, it's having also symmetrical, but through the 0, 0, right? You can imagine, I mean, this one and that one. This is, of course, symmetrical left and right. But for x cubed, we see that it's symmetrical through this. You can reflect to the left and then reflect downwards, right? So we say that even function is symmetric about y-axis. And then we go for the asymptotes. So asymptotes, we can check maybe the horizontal one first. So horizontal, how to check? We take the limit, and then take x to infinity. And you will see that this is going to be 2, right? Any question why it's 2? Raise your hand if you don't know why it's 2. Okay. Let me open this up. A little bit review on limit. So whenever we have this, what we are going to do, we are going to divide both numerator and denominator with the highest nominals, highest degree of polynomials, which is x squared in this case. Which results, this one is 2, this is 1, and this will be. And whenever we have 1 over x or 1 over x squared, when we take the limit going infinite, this will be getting 0, right? So that's why we have 2, okay? So it means that y equal to is our horizontal asymptote. I think the same way if we take to the left, to negative infinity, also the same y equal to, right? And then vertical asymptote. Remember, for the vertical asymptote, we are going to let the limit approach some value. And how to determine the values is based on our functions. Okay. So let the functions, let me write the functions, maybe let me just copy this one. We see that the most obvious component from this function is the denominator. That perhaps that is going to be our clue for our asymptote. Okay? So the x squared minus 1, we can see that it can be factorized and became x minus 1 and x plus 1, right? And these two, if x equal 1 or x negative 1, it makes our function become undefined, right? Define something with 0, right? Which means that the 1 or negative 1 will be our x approach for limit. Okay? So we take the limit as x approaching 1. Let's divide this from the right, okay, and from the left, so we can check both sides. So this will be infinity, right? This will be infinity. But how do we know it's positive or negative? We could try some number nearby 1 from the right, maybe 1.1. We put 1.1 here, and it is going to be larger than this one. It's positive. It's positive. Positive. Okay. I hope you get my idea. And then we can try 1 from the left. From the left of 1, you can think 0.99. Let's try 0.99. 0.99 squared, what is that? 0.9, 0.9. Will be less than 1, right? Yeah, less than 1, right? So it will be negative. So it's negative infinity. Okay. This will be negative infinity. The same way with the negative one. We check negative one from the right and from the left. Okay, if you check this, you can check negative 1, and from the right, it will be negative 0.99. Okay, 0.99. It will be the same as the negative infinity here, right? And this will be also this will be positive, right? Okay. So at the end of the day, x equal 1 and x equal negative 1 are vertical asymptote. Okay. So at least 1/3 of the question is solved. 1/3. Not yet derivative. So at least from this asymptote and all the domain and intercepts, when we draw the curve, we can draw this line first. So then we know the curve will, for example, if it is nearby the asymptote, it will not ever going to cross the asymptote, right? So we are having some boundaries. Okay, let me copy this. Okay, so domain, intercept, symmetry, asymptote, finish. Then we go for the first derivative and second derivative. Okay. Okay, let's go. So our function is this. Let me write y as a function of x, okay? Just to make sure that same with what we write in the notes. Okay? So take derivative. Do you still remember how to derive this? Okay. Thursday is your quiz. You better be remembering how to do it. Yeah, quotient rule, right? Okay. Okay. Okay, good. So it will be 4x, and then x squared minus 1, minus 2x squared, and then 2x right back, right? So I think, let me compute here. Yeah, we can cancel this. Yay. So negative 4x. This is f prime. So now how do we know which one is the maximum, minimum, critical numbers? The possible way is x is 0, and the other one, remember, what we need to include in our line number is also the one that makes it undefined. So perhaps we take this equal 0, which means that if this is 0, then x is 0, and x should not be equal to positive negative 1. Okay? So we have at least 3 numbers that is important within this first derivative. Okay? So 0 or negative 1, 0, and 1. And again, what we are going to do is checking whether the first derivative is positive or negative. Check the interval. I think we can check from the left part, which is negative. So check negative. Negative on the top will be positive. Negative here will be positive, positive, positive. Okay? Positive. So this will be positive. And how about negative 1 and 0? Then maybe half. Okay? Negative 1 over 2. Negative 1 over 2 here is positive. Negative 1 over 2 will become 1 over 4, which is less than 1, which is negative. Negative, positive. It's going to be positive, right? So let me check again. The negative half is 1 over 4. So negative squared is positive, positive, right? Positive. Okay. And then 0, 1 is, let's say, half. So half. So it's negative. Negative on the top. This is negative, but squared. So positive. So negative, positive, it's negative. Okay? And then try x equal to. Equal to, the bottom part will be positive, and the top one will be negative, right? So it will be negative. So it will increase, decrease, decrease. Okay? And then you could sort of imagine that this will be your vertical asymptote also, right? 1 and negative 1. So perhaps it will be going that, and then this will be maybe still going there. So this is asymptote. And then maybe this is going down like that, perhaps. And then the question is, the critical number is only 0, right? Only this x equals 0, right? So we could say, if you want to know the value for the minimum or maximum, or here is maximum, right? So 0 is, this is local max. So F0 is, copy this right here. So this will be 0, okay, which we are going to already proven that this is the intercepts. Okay, 0, 0 is the intercept. Okay, what's next? The next is, let me write the first derivative is this. Let me copy this right here. Now we can check the concavity. Okay, the concavity. So check concavity with the second derivative. Okay, make a little bit long. And then this will be 4. This will be negative 4. X squared minus 1 squared, right? And then minus, let me make a bracket to avoid mistakes. So negative 4x, and then multiply with 2 x squared minus 1 multiplied by 2x. Okay, what is this now? 4x is negative 4x squared, or 16, and then x squared minus 1, right? Or no, right? So okay, still Okay, whenever you find like some difficulty in math, like you think like, oh no, it's too long, too complicated, too complex. Okay, don't give up. Okay, slowly but sure, try to see things from different perspectives. Okay, somehow you will be able to do it. Okay, so just write here x squared minus 1 squared plus 16 x squared minus 1. My suggestion here, whenever you have like complicated expansion with half square or cube or with power of 4, do not expand first, okay? Unless you don't have any options, okay? If you don't have any option, then you can expand. But here we see that we can have the same components, right? So we can factorize this. Okay, and let's factorize it. So we can factorize x squared minus 1. This will be negative 4 x squared minus 1, and then plus 16x squared. Okay, we can cancel this part with this, so become 3. So our final second derivative is, now we can compute this. This is minus 4 plus 4. This will be 16 minus 4 will be 12. 12x squared plus 4 divided by x squared minus 1 cubed. Okay? So finally, we got something really nice here. From something really like hell, and then we get something nice. Okay? So slowly but sure, and my suggestion again, this squared here, do not try to multiply and expand first. Okay, do not ever do that. Okay. Okay. Sometimes like students, they are too naive. Like, oh yeah, okay, expand this, and then you are wasting your time. Okay, you need to do better, smarter. Okay. Okay, we have this now. Now what we can do from the second derivative? The same as we did before. We might think that there might be an inflection point, maybe. So let's say this is going to be equal 0. So let's try that one first. We could imagine that this is going to be 0, but if we think through, it's negative 1 over 3. X squared equals negative 1 over 3. So it's okay because it's not a real number. So we say that this is not real number. So we're gonna start from there. What we are going to do is this part on the top is always positive. Do you agree? Any number you put here, it's always positive. 0, negative, positive, all will be positive, right? Because it's squared and then it's plus 4. So it's always positive. Okay. Let me write here. Since 12x squared plus 4 always positive, okay? To make the f double prime x or less 0, it depends on the denominator. Or maybe just x squared minus 1 is okay. Because we are going to take the cube. So we are going to, I think I will make it small. Okay, make it small here. There you go. Okay. And then make it here. So we are going to see that at least we are going to have that the x will depend on 1 and -1. But since 1 and -1 is also our asymptote, we're going to check the intervals as well. So check the intervals from -1 and 1. Okay. So check for the f prime. Okay, check for the f prime. So maybe check from the middle. From 0, 0, -1, cube. -1 cube is negative. So negative positive is negative. Okay. So negative. So it means that this will be concave downwards. Okay. And check the left one will be, let's say -2. -2 is become 4, positive, positive. Positive, check the number, the last one, the right, x equal 2. So it will be positive, positive, right? Okay, agree? So I can say that this will be positive and positive. So this is concave upwards, concave upwards. Oh, we see that it's concave upwards, concave downwards. Inflection point. Or no? Do you agree if this is inflection point? It's changing concavity, right? Do you agree? No? Why? Yeah, it's the asymptote. So, okay. Whenever you find the asymptote and you see the same number in the line number, my suggestion is perhaps from the first one here, you could somehow maybe just drawing like this. So you know that, oh, this is the asymptote. And here also you can draw. So whenever something happened there, like maybe it is becoming maximum, minimum, something similar to maximum, minimum, or similar to this. Oh, it's concave upward, concave downward. And if you don't think carefully, you will see that, oh, this is inflection point. But remember, this is asymptote. So no inflection point, okay? No inflection point. So no inflection point. No inflection point, but we know that this will be upwards and downwards and upwards. Now, the last one is to sketch. I will write all the summary from the first derivative, second derivative, also the asymptote. Okay. So I will write all into the new page. Do you need to write this? Still need to write this one? Can I move to the next page? I think the difficult part is if you have this fractal function and what you will do from this. You need to have good observation on function. If you have this, you need to imagine like what will happen on the denominator, what will happen on the top. And can we make it equal to 0? And there's something like that. So there's some possibility. It can be like, for example, in some cases you can make it equal to 0 and you can find like the one that make it 0. And maybe that will be the inflection point. But again, check the line number. Check it. Okay, so let me copy this. So this is the first derivative test. And then the second one. This is second derivative. And then all the asymptote So vertical asymptote is, or let me write asymptote, x equal 1, x equal negative 1. Horizontal asymptote is y equal 2. Okay. And then we take maybe here and maybe there our asymptote. This is x equal negative 1, 1, and then maybe there. This will be y equal 2. L, intercept. Forget intercept. Intercept is on 0, 0, right? Our 0 is local max. So 0 is this one here, right? 0, 0. It should be maximum here. So we should expect that like that, okay? And then we could confirm through the concavity, which this is concave downwards, right? 0 is in this concave downwards, right? Which means this estimation are true. So let's just draw that. Okay. And then from this interval here should be concave upward. This is also concave upward. And then we see that it's positive, positive. We have already positive, positive there. So we expect that this is going to be going up, going up, going down, going down. Precisely the same as the first drift. Up, up, down, down. And then is it, because of the asymptote, we are going to see that it's going to be like that. Okay. And this will be and that is our graph. Okay, finish. So this is the graph of y equal to x squared over x squared minus 1. From all the conclusions, the asymptotes, the first derivative, the second derivative, we can draw a conclusion to our graph. Okay? Any questions?
Are we gonna do some bench test?
Yes. Midterm, yes. Quiz now.
What is the midterm?
I think to be safe, it will be about 9. Around 9. Yeah.
There's still some downtime. Can I also
November 9. November 9. I think that will be your midterm, okay? November 9. To be safe, okay? You don't have any midterm that week, right?
probarlo con cualquier escuela de derecho, pero ambos son negativos. De ambos lados, todo.
Okay, finish.